The velocity of slip. If a sliding joint is between two bodies and neither is ground, velocity analysis is more complicated. As an example, we have this 4-bar linkage where the sliding link, link 3, is connected to the crank, putting the sliding joint on link 4. And link 4, as you can see, is not ground, but another link which is pinned to ground at this point. So link 4 is able to rotate. This is not our traditional 4-bar crank slider, which we're used to doing velocity analysis for, but today we will learn how to do velocity analysis for linkages where that sliding joint is on a link that is itself not ground. Here we have another example of a linkage that has a sliding joint here, which is on a link, in this case link 4, which is not pinned to ground. As you can tell, link 4 in this particular case is kind of a funny looking L-shaped link. You may recall that it really doesn't matter what the shape of a linkage is. We can work with it. We know that links come in all different shapes and sizes. But oftentimes what is most important is that link or that length that exists for the link between two joints. In this particular case, we call that the effective link 4. It goes from the joint here, which is joint A, to the joint over here, which is joint 04. So at this particular time, this effective link has a length from 04 to A. But that length, will change as this crank rotates in the direction shown, which is clockwise for the angular velocity omega 2. We also have some other vectors on this page, which I'm going to describe in more detail in the next slide. But suffice it to say now that this vector here, VA2, is the known value. This is a 1 degree of freedom system, and VA2 is known because omega 2 is known. And from VA2, we'll be able to determine VA4, which is shown as a right angle to our effective link 4, and VA42, which is tangent to the slot. We'll also be using a velocity vector triangle that we are used to from other types of velocity analysis. So, some velocity expressions that we have for this particular linkage. At point A, which is right here, we have A on link 2. So this point A is on link 2, which is our crank, which gives us the velocity vector VA2. VA2 simply means the velocity of A on link 2. It is at a right angle to our crank, and it goes in this direction because the angular velocity is clockwise. If the angular velocity had been counterclockwise, we'd expect VA2 to go in this direction. We also have point A existing on link 3, which is the piston. For that, we have a velocity VA3, which in this particular example is equal to VA2 because, again, A is on link 3, and link 3 moves in the same manner that link 2 moves. As the crank rotates in this direction, so does go link 3. And finally, we have A on link 4, VA4. VA4 is again drawn at a right angle from the effective link 4. It also could have been drawn in the opposite direction if our angular velocity had been counterclockwise. In this case, we start off knowing VA2 from the given input angular velocity omega 2, such that VA2 is equal to omega 2 L2, L2 being the length of our crank. We then can use the velocity addition equation, VA4 equals VA2 plus VA42, to solve for our other unknown velocities in our system, which are VA42 and VA4. Notice our velocity vector equation, or our velocity vector triangle, where VA2 is a absolute vector, which we add to it VA42, and thereby get VA4. You may recall that we can separate VA42 and call it VA4 minus VA2, in which case the VA2s would cancel and we'd have VA4 on both sides of the equal sign. Now, on this particular figure, we have some other vectors drawn, and it's a good time to talk about some different definitions. VA42 is simply the sliding velocity. This is a term that we will often solve for in velocity of slip problems. The sliding velocity is along the slot. It is directed tangent to the slot, even for curved slots. And so this slot that we're dealing with here is a straight slot, but even if it had been a curved slot, perhaps some kind of semicircle, still the velocity of slip would have been tangent to that curve at that location. We also have an axis of slip. It is going to be tangent to the slider motion, and for these problems we will always assume no friction in the slide joint. We also have an axis of transmission. The axis of transmission is perpendicular to the axis of slip and is the direction of force and motion transmission for the mechanism. We have two projections here. We have a VA4 slip, which is a projection of VA4 onto the axis of slip, and we have a VA2 slip, which is a projection of VA2 onto the axis of slip. Now we're going to do an example problems where we can solve for the angular velocity, omega 4, which is found from VA4, and we'll also solve for the slip velocity, which is here called V slip 42, but before we talked about it as VA42. So these two terms, or these two variables, are interchangeable. We're going to perform the velocity analysis on this particular mechanism here. So, to perform velocity analysis, we're going to use a vector triangle, but first, it is important that we recall that whenever we do velocity analysis, position analysis has already been done. So for this particular problem, it means that we start off knowing our input angle, theta 2, our slide angle, theta slide, and our effective length 4 angle, theta 4. So before we ever begin to do velocity analysis, we would have already done the position analysis, which enabled us to determine theta 4 and theta slide given theta 2. Now we can proceed with our velocity analysis, where we've already said that VA4 is equal to VA2 plus VA42. VA2 again is equal to omega 2 times O2A. O2A could also be called L2. Here's our velocity vector addition triangle, where VA2 plus VA42 equals VA4. Again, VA2 is an absolute vector coming from the origin, as is VA4, whereas VA42 is a relative velocity vector. If we could determine the angles within this triangle, knowing already one of the sides, VA2, we could find the other velocities, VA42, which is one of the things that we were asked to solve for, and VA4, which will enable us to solve for the angular velocity omega 4. Well, it helps if we realize that these angles, which I'll label E, F, and G, can all be found from within the triangle shown here, VA4, V slip 42, and VA2, once we have determined theta 2, theta slide, and theta 4 from position analysis. So let's use these new coordinate systems to help us. So here's a horizontal X. Notice this horizontal is the same horizontal that we see in many different locations, and a vertical Y. This angle here in green, the angle here in blue, and the angle pink are going to help us determine E, G, and F. Here are those angles put onto our large velocity vector triangle. And as we can see, our angle A should be equal to theta 4, which we see here, minus 90 or plus 90. So depending upon the direction of motion for theta 4, we'd expect VA4 to either go in this direction or in this direction. If it was to go in this direction, that would be theta 4 plus 90, whereas in this direction would be theta 4 minus 90. But since our angular velocity, omega 2, is in the clockwise direction, we know that that's going to move length 4 in this direction, so VA4 is equal to, so this angle A is equal to theta 4 minus 90. Next we have angle B. Angle B is that angle which orients VA2. And here we see VA2. So VA2 should be theta 2 either plus 90 or minus 90. Again, since we see omega 2 as clockwise, we know VA2 goes in this direction, which means it's theta 2 minus 90 for angle B. And finally, we have angle C, and angle C is our slide angle, and that's the angle which positions VA42. Again, it's important that we remember that these three angles, theta 4, theta 2, and theta slide, are all from position analysis. And so angle A, angle B, and angle C can be determined. Now, we'll solve for the lengths and angles of the vector triangle. Remember, VA2 is our known length. We are here solving for VA4 and VA42 using the angles shown and some sine laws, or I should say, and the sine law. So angle E is equal to angle A plus angle B. From the previous slide, we'll find that that is equal to theta 4 plus theta 2 minus 180. Angle F is equal to 180 minus angle B minus angle C. But from the previous slide, we found that angle B was equal to theta 2 minus 90, and theta C was the theta slide angle. And so angle F is equal to 270 degrees minus theta 2 minus theta slide. And finally, angle G would just be 180 minus the other two angles. Now we're ready to apply the sine law. On the right-hand side, we have our knowns. VA2, again, a known length equal to omega 2 times L2, under the sine of its opposite, which is the angle G. On the left-hand side, we have sine of the angle E and its opposite, VA42. So now we're able to solve for our slip velocity, VA42, by simply getting the other side, VA2 times the sine of angle E over the sine of angle G. So we've solved for the first part of the first velocity we were asked to solve for. We will apply sine law again, same known on our right-hand side, but on our left-hand side, we'll use the sine of angle F and VA4. Knowing VA4, we can then solve for omega 4. So omega 4 would be equal to VA4 divided by length 4, or O4A. It's important to also recognize that omega 4 and omega 3 have the same angular velocity. That is because the piston, or length 3, is within length 4, and so they must rotate together. And so now we've solved for both of our unknowns. We've solved for omega 4 and VA42, our slip velocity. And that's the conclusion of our introduction to slip velocity.